form of a sphere. So when we're integrating over a solid in the form of a sphere, we can certainly use cylindrical coordinates, but if we had something that would be more associated with a sphere, that might make things a little bit easier for us. And so the idea is to take a look at the whole sphere, pieces of the sphere. As long as it's a spherical looking thing, we can try to describe it with what we're going to call spherical coordinates. Now the coordinate system is going to change from x, y, and z into something else. Now in cylindrical coordinates, we went from x into r and theta. Well, x and y into r and theta, and then z remained the same. So if we were to take a look at this in Cartesian coordinates or in rectangular coordinates, we would have not so nice looking functions all over the place. So let's say we had a circle or a sphere, radius 1. And then we integrated with respect to z and then y and then x. We would have the two hemispheres, the bottom hemisphere and the top hemisphere, and then we look at the shadow on the xy plane. We essentially have a circle of radius 1. And then we would kind of set up our equation, not very nice looking, but it'll look something like this, our limits of integration. But now if you go into cylindrical coordinates, we saw how that transferred, where the z is still going to be the z, except the x and y turns into r and theta. And so if we take a look at this transformation, the z will remain a z, except we have that relationship with x squared plus y squared is equal to r squared. But at least in 2 dimensions, we'll have nicer limits of integration. We'll have constant limits. So what we want to do in spherical coordinates ideally is to have variables, and I'm going to put stars for these variables, where all these values are constants. Because if all of them are constants, then that would ideally be a lot easier to integrate. So we came close with cylindrical coordinates, but cylindrical coordinates doesn't really take care of the spherical part. because the z is just equal to z. So what we want to do now is change it so that it becomes something that would be with the sphere. And so we need another transformation. Now remember that the r is just on the xy plane. Since we're talking about spheres, it would be nice to talk about a radial distance from the origin out to any direction that's not just flat on the xy plane. Right? So we want to find another radial distance like that that would describe some distance from the origin. And then aside from that, I think we're just going to go with angles. So I should just give you the transformation. I guess before I do give you the transformation, because when you think about the transformation, you might easily forget it. And so let's see if I can try to make you remember the transformation by assigning something different here. So this is the point I want to represent as my XYZ point. And what I want to do is I want to call this green vector something. Let's call this green vector the Greek letter R for radius, except it looks like a P. This is called rho. So let's call this distance, the radial distance from the origin out to somewhere in space. Let's call that rho. Now, from cylindrical coordinates, I kind of remember this to be R, right, on the xy plane. And then this is theta. So I don't know if I need to use R anymore. But theta might be an important angle, and rho might be an important length. So I need one more variable to describe. Okay, we can look at the angle from the xy plane to there, but actually that's not the angle we're going to look at. But that would be nice, actually. I think that would be the first natural thing to consider. But instead of that, what we'll do, instead of looking at the angle from the xy plane, what we'll do is we're going to look at the angle from the positive z-axis. So if it's on the xy plane, you can have it go up and down, then that would introduce positives and negatives. But if we have it from the positive z-axis, it might be good to just measure from there going down, and then that will always be some positive angle. So this angle here, we'll call phi. Some people call it phi. Other people call it pho and bum. But that's an angle from the positive z-axis. Yeah?
So
It's from the origin going out to anywhere.
So it's
Any direction, because now we're introducing phi, and then we're also introducing theta.
so it'd be the angle. So theta would be the angle from the xy plane, and the phi will be the angle from the green vector to the z-axis.
To the positive z-axis, yes. Yes.
So is it always positive?
Yeah. So that would make things always positive, because if you go in, it doesn't make sense to go in a negative, because your theta will spin you around to the appropriate spot.
Oh, okay. So since theta is always positive.
And theta goes from 0 to 2 pi. Phi, what do you think phi is going to go from? 0 to pi. If pi over 2, you stop at the xy plane. But if you go all the way down, and you can go all the way down, you can go all the way down to pi. But you wouldn't go past pi, because that'll loop you around to the other side. But theta is going to handle the going around on the xy plane. Imagine going past pi. And if you go past pi, you can really get that with a different angle of theta. So anyways, maybe I should have done this on another page. I wasn't going to make a big deal out of this, but now it's getting to be kind of a big deal. So what I wanted to do is so I have 1, 2, 3, 4. There's 4 variables here, and clearly you want to just do 3. And I think I want to get rid of r. And so what we're going to try to do is we're going to try to express the different values of x, y, and z in terms of everything here except for r. So what we have is x is equal to, from cylindrical coordinates, x is equal to r cosine theta. Right? But remember, I want to get rid of r. So let's see if I can find r from this picture. I'm going to draw the same r distance up here so I can look at the triangle a little bit differently. And if I look at those components, I hope I got everything there, right? So that point, x, y, z, will kind of revolve around this triangle. This triangle, I just straightened out this triangle with the green phi, or rho, the green rho. The black line over here is the axis, z-axis. And then the height of that triangle is going to be the z component. And then that purple line over here is the measurement of r from cylindrical coordinates. So if I want to replace r with something, and here's one of the keys, we're going to replace r with something. What are we going to replace r with based on this triangle with phi and rho? Something about opposite over is that the opposite over hypotenuse? R is equal to what? Rho sine phi. And Z is equal to what? Z is the adjacent side, right, of the angle. So Z is what? Rho times cosine phi. So that's what we're going to do. Just replace the x, y's, and z's with everything with rho, phi, and theta. Now we're going to replace the r with rho sine phi times, there's a cosine theta next to it. And then the same thing with the y, we're going to replace r sine theta, we're going to replace the r with rho sine phi and then sine theta. And then we have the z to equal rho cosine phi. That is our magic substitution. And the way I remember it is the y is a sine and a sine. So it's a combination of sines and cosines. The y is a sine and a sine. The x has a cosine theta from r cosine theta in cylindrical or polar coordinates. So, and if you just remember that once upon a time, this rho sine phi was equal to r, then you have a better chance of remembering this formula off the top of your head. Of course, for the test, you'll just write it down. It doesn't matter. All right. Now, it also happened that x squared plus y squared plus z squared is equal to rho squared. That's what makes it a solid formula for us now to go in the cylindrical coordinates, or spherical coordinates, because everything described here is going to be associated with a sphere. Now, we are dealing with triple integrals here, and so we're going to need a triple integral transformation for our dv, our differential, our dx, dy, dz. That has to be replaced. And so for that, we call on the formula for the Jacobian again. This time, our functions of x, y, z get transformed into the new variables. We'll call it rho, phi, and theta. And let me set up the matrix. We got x with respect to rho, x with respect to phi, x with respect to theta, y with respect to rho, y with respect to phi, and y with respect to theta, and then z with respect to rho, z with respect to phi, and z with respect to theta. And now these are the functions that we would take derivatives of. I'm just going to do one more step and write out the big matrix, but it could take a while to actually compute the determinant. So let's see if we can just take the partials. So with respect to rho, the first one with respect to rho would be sine phi cosine theta. That's the first slot. X with respect to phi, derivative of sine is cosine, so it's rho cosine phi cosine theta. And then the derivative of this thing with respect to theta, it's negative sine. So we do the same thing for y. And then we do the same thing for z. Okay, so we expand on that and we do things to it. We'll get a bunch of sine squared plus cosine squared combinations and things, and it'll all just simplify to rho squared sine phi. Okay? So whenever you change into spherical coordinates, this is going to be the transformation that will come out. And so your integral will have this as your transformation. Okay? So if we take a look at that first example where we took a look at a sphere radius 1, let's imagine how we're going to construct this integral if we're integrating over this E in terms of spherical coordinates. So it's a sphere. And we should expect it to have constant limits here. And the radial distance goes from 0 to whatever comes up to, 0 to 1. Our phi goes from the positive z-axis down to the negative z-axis. And remember, we don't want to go past pi, because if you go past pi, then you're kind of repeating yourself. And that's if you let theta go from 0 all the way around to 2 pi. Now with the sphere, you have constant limits. Better, certainly better than rectangular coordinates, and then better than the spherical coordinates that we saw. And any piece of this sphere can be described with rho, phi, and theta with constant limits if it's going to be still going to be sphere-like. Okay? All right, I have a graphic here that can try to describe what it is we're talking about. So let's see, what's A? What's B? C. Okay. So C is like rho. Let's get this to stop spinning. Okay, so B is like theta. So if you have theta, you can imagine theta as a measurement that goes around the xy plane. That's theta. A is like phi. If you have phi, you can imagine that as an angle from the positive z-axis going down. And then the rho is the radial distance, and this one I have it's the radial distance going from the bottom to some other value, which is probably 1 or 2. So if you just want something in the first octant, what's pi over 2 about? 1.7? 1.5? And then if I let my angle phi go from 0 to pi over 2, I'll get like a quarter of this sphere, or an eighth of the sphere, an eighth of the sphere. If I let phi only go up to like pi over 4, I would get a piece of a cone. And then if I let the rho go from some value to 2, okay, so the phi is between 0 and pi, because if we let phi go a little bit further than that, it'll be too much. Okay, so you have the idea of how to trace this out. Maybe we'll practice a little bit and we'll come back and take a look at this picture. So let's take a look at some examples. So let's do an example where we take a look at an integral already set up in spherical coordinates, and then we'll see if we can describe the shape. So I'm not too interested in evaluating the integral. So I am just concerned about looking at what the shape looks like. So kind of like what we did before with the x, y, and z, we want to match up the limits of integration and then try to imagine how this thing might look like. So it looks like our rho goes from 3 to 5. Our phi goes from pi over 2 to pi, and then our theta goes from 0 to 2 pi. Now let's think about this. Theta goes all the way around. A row goes from 3 to 5. How would you imagine a row going 3 to 5? How would that look like? It's like a washer, right? Except it's three-dimensional. So, that's like what? No, because it's actually spherical. It's a hollowed sphere. It's a sphere with a hole in it. With a sphere taken out of it. Now, this part over here, phi, remember it's a positive z-axis measurement. So from the positive z-axis, you actually don't start at 0, you start at pi over 2. Where's pi over 2? Well, yeah, what angle are we looking at for pi over 2? It's the xy plane. So we start with the xy plane, and then we go all the way down to the negative z-axis. And then this thing goes from 0 to 2 pi. Goes all the way around. Can you picture it yet? All right, let's take a look at this row. Right? And then now your phi goes from pi over 2 to pi. And then your theta goes from 0 all the way around to 2 pi. So it looks like a bottom part of a cup, except it's a spherical cup. Does that make sense? Does it look cool or what? It's exciting, isn't it? Yeah, sometimes. So, if you had choices here, which one would you choose? You have to look at the X, Y's, and Z's here. So it looks like Z is going up and down for all of these, which is good. Which one of these would work for us? Which one did I just draw? The bottom right, right? Okay. Except here they elongated along the z-axis, so it doesn't look like a sphere, but it actually should be a sphere. So let's do one more thing. Since we do know some geometry, we can call this volume E, right? And then this integral is actually the triple integral over E. Now it looks like rho squared sine phi is part of the dV business, right? Does that make sense? We're kind of working backwards here. And so, do you remember what this gives you? If your integrand is 1? Volume of E, right? So this has radius 5 and radius 3. It looks like it's half of a sphere that's been dug out. Do you know what the volume of the sphere is? What is it? So this is our volume for a sphere. It looks like if we take the whole sphere of radius 5, and then we take out the sphere inside of radius 3, and then we cut it in half, we would get the answer without doing an integral. Wow, that's kind of cool. Let's see if we get it right. So we take half of the sphere, take a sphere of radius 5, and then we take out a sphere of radius 3. And then we take half of it. Let's see. 4/3, this would cancel. We get 2/3 pi. And then we got 125 minus 27, 98. That's not divisible by 3, so what's 98 times 2? 180, 196. Oh, let's see if we get it right. So there's a nice trick to this. If you can identify these integrals that are just looking for some geometry, and you know your geometry, like finding a volume of the sphere, finding the volume of the cylinder, or stuff like that, then you should be able to get it without doing any integrals. We just did this problem where we're supposed to integrate something. We didn't integrate anything. We got the right answer. That's pretty cool, huh? Now you're kind of just wielding power over calculus. All right, let's try another one. Now this one looks like it's in cylindrical coordinates. Let's not do that one. This one looks like it's in spherical coordinates. Let's try this one. All right, so we got this thing set up. This is the solid that we want to integrate over. We have, we're doing it in spherical coordinates. So already our dv should get replaced with something, and so this should be rho squared sine phi. And then this would be your, whatever your x is, your y is, and your z is, right? So this is rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. So those are all regular. And so this is what we're really should be kind of focused on. And what we want to do is we want to take a look at how this is going to look in terms of our inequalities for the rho, phi, and theta. So because it's another one of those spheres with a hole in it, I want to think about that as the radii of those spheres. And we're going from the smaller radius to the larger radius. So that part I think is easy. It's going to go from 3 to 8. So our d rho is the inner integral. That's going to go from 3 to 8. Now our phi, I have my phi second, but it looks like they have their theta second, but it doesn't matter because it's all constant. So I'm going to do my phi first. And our phi limits go from the positive z-axis to, how far down did I go? Just pi over 2. So right along the positive z-axis is where you'll have an angle of 0, and then you'll have an angle of pi over 2 to be the maximum value. So 0 to pi over 2 is our limit, our limits for phi. Now theta, it might be good to look at this flat. If you could see it in 3 dimensions, that's great. You can see it going around, right, from the positive y-axis around to its negative side to the positive x-axis. But if you can't see that right away, just redraw your x and your y into perspective here. So this is where it starts in the positive y-axis, and then you go around on the negative side of that to the positive x-axis. And so the question is, what are these angles? So you have an angle over here, pi over 2, to begin with, and then you go all the way to 2 pi, and that should be the top limit. Okay? Any questions? All right, let me talk a little bit about a cone. And most of the cones that we've been dealing with have been x squared plus y squared. Right? And so this is the positive part of the cone. But it turns out if you multiply this by anything, it's still going to be a cone. Yeah? Yeah, square root. Sorry. Should we put the 3 under square root? It doesn't matter. So let me just show you some cones. So the cones are generally going to be drawn with whatever constants that you have out here. I have this n values going from negative to positive, so a negative constant in front of that will put you down as a cone facing downward, and a positive constant would have a cone facing upward. But you can also have your cone going really small and steep, or kind of flatter. Okay, so this is close to 1, and if we get it flatter, like 0.3, it's still a little bit of a cone, right? So these are all cones. And I drew these cones so that we could take a look at this from a from the perspective of polar or spherical coordinates. Because if we have a sphere and one of these cones intersecting it, then we can still find that. So let's say we had this cone, and then we had a sphere radius, I don't know, pick a number for a radius. Between the cone, z is equal to 3 squared of x squared plus y squared, and the sphere. x squared plus y squared plus z squared is equal to 2 squared, or 4. So if we want to find the volume of that, we would imagine that this is some sort of cone-like figure where I guess it would be a little steeper, and then your sphere would be whatever your sphere is going to have the radius of. So you're looking for the space in between here. Whoops. You're looking for the space in between here. So again, you can use rectangular coordinates or Cartesian coordinates or rectangular coordinates or cylindrical coordinates, but since we're talking about this thing as being part of the sphere, we can certainly use spherical coordinates. So using spherical coordinates, if your radius is 2 and there's no sphere being cut out of it, it looks like it's just going to go from 0 to 2. And your phi and your theta, and it looks like theta goes all the way around from 0 to 2 pi, so I'm going to put the theta limits now and focus more on the phi limits because that's where it gets a little bit different. So our phi limit, remember, goes from the positive z-axis down to however far this is going to go, and then our cone just kind of stops at some angle over here that it makes. So now the question is, what is that? What is your phi angle going to be? Well, we got to do a little bit of trig here, and what we have to do is we kind of need to flatten this, but not flatten it on the xy plane, flatten it on, I don't know, the xz or yz plane. So if we look at this on the yz plane, we have this part of the cone that goes like this. And if you get rid of, look at it on the yz plane, essentially you're setting x equal to 0. You're going to have z is equal to 3y. And it looks like 3 is going to be the slope. This is tangent of 3 or tangent inverse of 3, something like that. So what are we looking for? We're looking for this angle, and then if we just randomly stop this at some point somewhere, let's say when y is equal to 1, z is equal to 3, you're going to have your relationship with the opposite over adjacent. So the opposite is actually 1, and the adjacent is 3. So tangent of phi is going to be 1 over 3. So that's just the arctangent. So now you've found your angle phi that measures from the positive z-axis down to wherever that cone is. Okay? So you can set up this integral if you want. So remember, the triple integral over your volume dv is going to be the volume. Triple integral over a solid E dv is going to be the volume. So we're going to set up this triple integral in spherical coordinates. So our dv becomes rho squared sine phi And then we can choose to integrate with whatever we want first. We can integrate. These are all constants, by the way. Even the arctan of 1/3, that's just a number. So we can go d rho from 0 to 2, d phi from 0 to the arctan of 1/3, and then d theta from 0 to 2 pi. Okay. Any questions? All right, let's see if we can find a homework problem, your actual homework. Oh yeah, it is due November 8th. Yeah, we'll push it off to Sunday.
You're welcome to change that.
What? These look like homework. Maybe I thought they were labs. You guys can do stuff like this, right? Phi is equal to pi over 4. What is that? If phi is equal to pi over 4, then you're assuming your theta goes all the way around, and then your rho goes from 0 to infinity. What is it going to look like? So it's 45, and then it's been spun around. A plane? No. It's a cone, right? So phi goes down 45 degrees, and then you spin it around with no restrictions on rho. Rho can go from 0 all the way to infinity, and theta goes from 0 to 2 pi. In fact, if I type that in my graphing calculator program, I'm going to get a cone. Rho equals 5. What is that? Assuming your largest limits for phi would be going from 0 to pi, and then your theta goes from 0 to 2 pi. That would be what? Sphere, radius, 5. All right. Anything else interesting from your homework? Oh, we just did this. Ah. Ooh. Ooh. Look at this one. Bumpy sphere. Yeah. I don't know. You want to do any of these? Yeah. The donut problem? Use spherical coordinates to see whatever is more appropriate. Find the volume enclosed by this. So we're not going to talk much about this. I'm certainly not going to test you on it. But if you write rho as a function of phi and or theta, you're going to get some certain shapes of things. So asking you to find the volume of the enclosed torus, rho is equal to 4 sine phi. If you were to try to imagine what this thing might look like, there's no restrictions on theta. So you can imagine whatever this might look like if you were to try to draw it, say on the YZ plane or the XZ plane. It's going to spin around on the XY plane. It's going to spin around on the Z is equal to 0 axis. XY plane is better. So it's going to spin around on the XY plane. And so the other thing to try to relate this to is that this kind of looks like R is equal to, I don't know, cosine theta. You remember how that looked like? Or sine theta? This is one of these off-center circles. So that's what this is kind of. This whole business is kind of like this. So rho is equal to 4 sine phi. So if phi was equal to 0, rho would be equal to 0. If phi was equal to pi, and remember, phi is equal to pi, you'd be down here. Oh, that's too hard to graph. What I was going to say is that on the YZ axis, it'll kind of look like this circle, and this is probably going to be radius 2. This is 4. And then it's going to be spun around with no values on theta, except it'll probably go from 0 to 2 pi. So it's going to spin around. So that's when you get that donut shape. Anyways, to find the volume of this, we can imagine that we're just going to go from the usual limits. Again, there's no theta, so we're going to assume we're going to go all the way from 0 to 2 pi. And phi, it looks like we're going to take it from 0 to pi. And now our rho is going to be a measurement from 0 to whatever this function is. So because the original surface or the original solid was not a true sphere, we're not going to have all constant limits like in this case. So our rho turned out to be a function of phi, so we're not going to be able to integrate that by splitting it up like we've been able to do in the past. And then your integrand is 1 dv. So that changes in spherical coordinates. Rho squared sine phi. Let's integrate with respect to rho first from 0 to 4 sine phi. And then we'll integrate with respect to phi from 0 to pi. And then with respect to theta from 0 to 2 pi. Okay? Should we do it? Nah. Hey, it's an easy integral of rho squared over 3, and then you put 4 sine phi in it, and then you'll have a trig integral. If it's an even power, rho cubed, yep, it's going to be sine to the 4th power. You're going to have to, there's some more trickier trig substitution to take there. But you can punch it into Wolfram alpha and see what you get. So aside from that, I would be more interested in problems like maybe number 7 would be a good candidate for a test or a quiz problem. Okay. So tomorrow I want you to be able to get all these shapes between cylindrical coordinates and spherical coordinates, and how to play around with a rho, with a phi, with a theta, and then with the r in spherical coordinates, how that would change things as you try to imagine how these solids would look like. And then I'll give you guys a quiz tomorrow. All right. Test will be on Monday. The quiz will be on finding limits of integration from shapes. You have to be in class to take the quiz.